So I do want to, I've said everything, but I will just, so that you have it in your notes, because when we're just talking about it, you may not have written it down. Let's just be explicit about it. With the example I was talking about, but let's make it official. So we've already answered it, but let's answer it formally in our notes here. Why doesn't independence of the lambda on distance from the source violate the inverse square law? Consider observing the sun from 1 AU and 2 AU, which we did. Since the solid angle it subtends is omega of the sun is pi radius of the sun squared divided by the distance to the sun squared, which we'll call r squared, little r squared. At 2 AU it only subtends 1/4 the solid angle, but it does at 1 AU. Catch up with that. By the inverse square law, the flux of the detector is also 1/4 as large at 1 AU. Square law of the flux on the detector is also only 1/4 as large as at 1 AU. So the specific intensity which is the flux divided by the solid angle stays the same. Bang, it stays the same. Which is the point we were making. It's specific intensity stays the same because the solid angle falls at exactly the same rate that the flux does. Specific intensity is the ratio of the two. And we'll also throw in the stuff about the area of the image on the retina. The area of the image on the retina is focal length of eye squared times the solid angle that the sun makes at your location. Since the solid angle is the area divided by the focal length squared, as we were talking about before. So turn it around, the area is the focal length squared times the solid angle. So the surface brightness on the retina is that'll be the flux on your pupil times the area of your pupil. Flux falling on your pupil is watts per square meter on your pupil times how many square meters your pupil has. Flux on pupil times area of pupil. Of course, here we mean pupil as in opening of your eye, not pupil as in you are my pupils.
I prefer Padawans.
What?
I said I prefer Padawans.
Padawans, okay, yeah. I guess it does, like, you know, you're my peeps sounds okay, but you're my pupes doesn't sound good at all. So.
Sounds a little close to something else.
Yeah, good point.
Exactly. That's why I prefer Padawans.
Whoops, not Padawans, definitely, let's go with that.
So Padawans.
Yes, okay. Flux on pupil times area of pupil divided by the image area on the retina.
This should be. I feel like being a senior has been that filter kind of like just die.
Yeah. I mean, I do talk about a joke filter, you know.
Yeah.
Mine is pretty coarse. As in, not coarse as in coarse humor, just coarse as in I just let a lot of
Everything
things
kind of
through.
goes.
Yeah, right. Right, so I think I mentioned, like, you know, it's like I just throw things against the wall and see if they stick, right? So.
I've been doing that a lot more recently,
Yeah.
especially in the house. Genesis has noticed.
Oh, yeah.
I make jokes a lot like you. I just like something will happen and I'll say something and then just she'll like look at me like, really? Wow.
Yeah. Just
That's exactly it. Like, yeah. That's just the genius of subtle humor.
there you go. And so that'll be what I'm trying to say. Yeah. So that'll scale like because the image area on the retina is proportional to the solid angle, right? So this will scale like flux on what am I trying to say? Yeah, the flux on the pupil is the flux. Your pupil's like, you know, being the detector, you're like holding a piece of paper detecting light from the sun. So the flux over that, what's proportional to solid angle will look like the specific intensity, essentially. So this goes like specific intensity times the pupil area. point is, since specific intensity is independent of distance from the sun, assuming that your pupil always closes down to the same area when you're looking at the bright sun, which is a pretty reasonable approximation, it's equally dangerous to look at the sun everywhere, except you just burn small holes under the retina if you're further from the sun. Okay, any questions? So there's another interesting fact, which I think we mentioned this in observational, which is that it turns out that no optical system can increase the specific intensity of any object that you look at it with. So in other words, if I look at the Orion Nebula with a telescope, the specific intensity is exactly the same as with my eye. Specific intensity can't be altered, essentially. And what that translates into is that you cannot make the surface brightness any larger by looking at something with a telescope. So all you can do is make a larger image that has the same surface brightness as seen with the naked eye. So that's kind of sad, because what that means is that no matter how big a telescope I use, if I look at a galaxy, I can't make it have any higher surface brightness than it does with my naked eye. All I can do is make it cover a larger area on my retina with the same surface brightness it does with my naked eye. So it's impossible, no matter how big your telescope is, to ever look at a galaxy and have it look like a beautiful photograph does, because you're just not able to increase the surface brightness on your retina beyond what your naked eye can do. So the only way to improve that would be to make your pupils larger. And there are negative consequences to making your pupils larger. So yes.
Hypothetically, so if something like, if we look at the stars, since they're on resolution.
Yeah, they're essentially like, they're airy disks, so to speak, along with some rings around them. Yeah. Mm-hmm.
Hypothetically, if something was like on the border of that, and then we used a telescope, would it kind of be brighter because then it would be burning our retina?
So, yeah, imagine that you're getting further and further away from the sun in our solar system. Then, again, the surface brightness would stay constant as you moved away. Our angular resolution is about 1 minute of arc, roughly speaking, of your eye. And the sun's about 30 minutes of arc across. So you would hit that limit at about 30 AU from the sun, which is right around the distance of Pluto from the sun. So as seen from Pluto, the sun would be a barely resolvable point that still would be really painful to look at. It would look like a little chunk of what we see here on Earth. You still wouldn't be safe to look at it because you could burn your eye by looking at it. If you looked at it through a telescope, then it would become like, if you magnified it 30 times, it would be just like looking at the sun from Earth with your naked eye, is what it comes down to. If you were 60 AU from the sun, so that it was underneath your resolution limit to the naked eye, you put a telescope on there that has high enough angular resolution, and whoops, magnify it 60 times, whoops, now you've fried yourself, because again, it would become just like looking at it with your naked eye at Earth if you magnified it 60 times. So there, your naked eye would be safer than looking at it with the telescope. In terms of your naked eye, it would be a bit dimmer. The surface brightness would be a bit down compared to what it is with the naked eye seen from Earth. For very distant stars, they're below the angular resolution even with a telescope, and so it just doesn't matter either way. Except that looking through it through the telescope does make it look brighter because it covers the same area on your retina, but the telescope has more light collecting area. So if you look at Sirius through a telescope, it looks brighter than it does to the naked eye. because it's still that same size, not pinpoint, but area, disk, and rings and all that. Actually, that would be out in outer space on the ground. It's smeared out by atmospheric blurring. The image is essentially, essentially about the same size, but it's much brighter because of the fact that you collect more light. So if you look at something like a globular cluster, which is a bunch of individual stars, then yeah, they look brighter and brighter the bigger your telescope is. So globular clusters do look better and better the bigger the telescope you use, because you see individual pinpoints of stars, and those pinpoints get brighter and brighter essentially. But if you look at the Orion Nebula, the image doesn't get any brighter. Just all that changes is the larger the telescope, the bigger the maximum magnitude you can use, and still have it look just as bright as it does to the naked eye. But with things that consist of stars, it's different. So in principle, if you had enough angular resolution to see the stars in the galaxy, eventually you get to the point where you get it better because you're seeing the stars brighter. But the angular separation between stars and a distant galaxy is so small that that's not a realistic goal, is what it comes down to. Especially with atmospheric turbulence causing flurry. Okay? Any other questions? All right, so we wrote down what the Planck function was. I'm just going to go ahead and send this back up. And zoom the camera appropriately. So we wrote down what B lambda was, what Planck was able to theoretically obtain by quantizing the oscillators, the radiators. Now we realize it's better to think in terms of quantizing the light and photons. It was B lambda is, no, it's okay, this one. Okay. B lambda is, as a function of temperature, was 2h c squared over lambda to the 5th power e to the hc over lambda kt minus 1. And what I want to do now is write down what we call B nu. In other words, we can write down the Planck function in terms of frequency instead of wavelength. First, you might think, so remember, what's the relationship between wavelength and frequency for light waves? For any waves in general, for sinusoidal waves, if they travel with some speed and they have some wavelength and some frequency, what's the relation between them? So, they're inverse, right? So lambda is equal to what over what? Which one's on top? There's wave speed and frequency, which one's on top? You can get it from thinking about how it should work. You can also get it from, it's an inverse, so if it's wave speed or frequency that's going to be on the top or the bottom, if it's going to be inverse, wave speed has to be on the top, right? And then frequency has to be on the bottom. I can also get it from units. You can get it from just thinking how many waves pass by me in one period, anything like that. that, but it's lambda is equal to C over nu. At first you might think, all I need to do to get B nu as a function of time is substitute everywhere I see a lambda, put in C over nu. But that's wrong. That does not give you B nu. And the reason is that, remember that B lambda is the wavelength specific intensity. That sounded good. So there is B lambda as a function of lambda, and remember that B lambda d lambda is the number of watts per square meter per steradian. So if that's a little d lambda right there, B lambda d lambda equals watts per square meter per steradian that is coming out of a little patch of surface. If I did it in terms of B nu, so who knows what B nu looks like? So let's just make some kind of thing to be B nu. Then B nu d nu should also be watts per square meter per steradian. And here I should decorate between lambda and lambda plus d lambda. So B nu d nu should be watts per square meter per steradian between what and what?
Nu plus D.
Nu and nu plus d nu, right. Between nu and nu plus d nu. And the idea would be, if it's the same set of photons, we should get the same number. So in other words, these should be corresponding ranges of wavelength and frequency. For a given set of photons, so to speak, we should have the same number of watts per square meter per steradian. So we want corresponding ranges of d lambda and d nu. In other words, if we're saying like between 600 nanometers and 610 nanometers, the range of frequency should be whatever frequency corresponds to 600 nanometers and whatever frequency corresponds to 610 nanometers. Those are the things to be comparing to one another. See what I mean? Does that make sense? The range in lambda is, say, 600 nanometers, 610 nanometers. The corresponding range in frequency, I'll just say in nu, C over 600 nanometers to C over 610 nanometers. In other words, the frequency that corresponds to 600 nanometers and the frequency that corresponds to 610 nanometers. So one thing is, what's bigger, C over 600 or C over 610? C over 600 is bigger, right? So in other words, it's going backwards. In other words, 6 to 610 is the order of increasing wavelength. It's the other way around for frequency. C over 610 to C over 600 is the direction of increasing frequency. So there's going to be a minus sign in there that we need to worry slightly about. Now, while in principle, you could do like C over lambda 1 and C over lambda 2, we're considering little ranges, and so we want to think in terms of differentials. So in other words, what we want to do is do this. We set B nu of T B nu, and I'll put an absolute value sign around the d nu to say I just care the total range in frequency, not whether I'm going from a lower frequency to a higher frequency or vice versa, is equal to B lambda of T absolute value of d lambda, where d nu corresponds to d lambda. And by that again, I mean we're talking about the same range of photons. The same range of photon wavelengths, just put in terms of photon frequency. Photons between the same two wavelengths, but expressed in terms of frequency instead of wavelength. So in other words, B nu is equal to B lambda times the absolute value of d lambda d nu. In other words, what this means is not only do I substitute C over nu for all the lambdas in my expression for d lambda, I also have to multiply by the absolute value of d lambda d nu in order to get B sub nu. There's more to it than just substituting. You don't put happy on it.
Is there no way we have to do this?
There's something in the homework, yeah. But it's actually in the homework what you're going to do is once you've got B nu, you're going to figure out where its maximum is. But you should understand where it's coming from. And what we're doing is deriving the expression for B nu. So it's a subtle thing to understand why B nu is not just put lambda equals C over nu for all the lambdas in there. That's not enough. You also have to multiply by this correction factor due to the fact that put it another way, keep it in terms of wavelengths in meters and frequencies in, what are the units for frequency? For SI, MKS, meters, kilograms, seconds, what are frequency units? Hertz, or fundamentally in terms of seconds, they are 1 hertz is 1 inverse second, 1 second to the minus 1. The point here is that what's d lambda for this range, if I went from, okay, this is 600 nanometers to 610, right, just stick to SI. So what if I went from, I'll be radio waves, 600 meters to 601 meters? What would be d lambda for that range of wavelengths?
1.
1 meter, right? d lambda is 1 meter. Do you think if I put that in terms of frequency that d nu is 1 inverse second? Right? d lambda is 1 meter, but d nu is not 1 inverse second. It's not 1 hertz. They're not the same. The differentials involved are not the same. So if I just substituted the C over nus for all the lambdas, I can't just multiply by 1 hertz to figure out how much radiation is coming in this 1 meter range of wavelengths. I can't say, well, that's a 1 hertz range of frequencies. It's some different range of frequencies. And that's why we need to make this correction, because it would have to be, well, what range of frequencies, what range of hertz how many hertz corresponds to that 1 meter change in wavelengths? And so when I do this correction, I need to do that figuring. What d nu corresponds to that range in d lambda. Put another way, you could say that b nu d nu is b lambda times, what do I want to say? B nu d nu is it's making me go backwards here. B lambda d lambda times d nu d lambda, get myself in trouble. This is the right answer right there. If I thought about it for a moment, it would work out, but I don't think not. So this is representing that correction. So let's do it, shall we? Lambda is C over nu. So what's d lambda? In terms of d nu. This is how we make that correction. For small range d lambda, this tells us it's a small range d nu. So if lambda is C over nu, then d lambda is, this is just differentiation, taking differentials.
C over d nu?
No. Maybe it's
C over d nu.
right, think of taking a derivative, right? So this will be minus C over nu squared d nu. Right, minus C over nu squared d nu. Because nu to the minus 1 differentiates to minus nu to the minus 2. So minus C over nu squared d nu. So that says, since we want everything to be positive, the absolute value of d lambda d nu is C divided by nu squared. So B nu is B lambda expressed in terms of nu. In other words, do make the substitution C over nu for all the lambdas. But then we have to multiply that result by C over nu squared to do that correction of the ranges. So B nu is 2hc squared over lambda to the 5th, but that's C over nu to the 5th power. So I am making the substitution to write B nu written in terms of, to write B lambda written in terms of nu, over e to the hc over lambda kt is e to the h nu over kt minus 1 times that correction factor of c over nu squared. So that says B nu is 2h nu cubed over c squared over e to the h nu over kt minus 1. That's the expression for B nu. So notice that it has a different functional form. If you plot b as a function of nu, it doesn't look like b as a function of lambda does. The curve has a different shape because b as a function of lambda has 1 over lambda to the 5th divided by e to the something over lambda minus 1. But b nu has nu cubed, and it's e to the something times nu minus 1. So they have different functional forms. B nu has a different shape than b lambda does. And your task, since at least some of you already found the maximum of b lambda in physics 280, is to find the maximum of b nu. And it's a very similar thing. Yes?
Can you explain how you get the nu cubed over c squared?
Because here we have nu to the 5th power, which is in the denominator. So right, this is divided by c over nu to the 5th power. So I'm going to have nu to the 5th in the numerator from that, and I'm dividing by nu squared.
Oh.
So I get 2 cubed up in the numerator.
Okay.
So that's worthy of some thinking, you know, to be sure you understand that conversion factor. It's one of those things that you do need to kind of sit down yourself and be sure that you really understand the logic behind all that. Relation between flux and specific intensity. So if you notice, our expression for b lambda doesn't have any angles in it or anything like that. It's isotropic. It's independent of direction. A black body is equally good at radiating in every direction. It doesn't radiate more in some directions than in other directions. To find the, this is a better word for it, the monochromatic flux. I mean, sometimes it's called the wavelength specific flux, but then if you talk about specific intensity, we don't really want to talk about the wavelength specific intensity. That's too many specifics. The monochromatic flux F sub lambda, whereas we were saying before the total flux, the thing that shows up in the Stefan-Boltzmann law, is the integral over all wavelengths of F lambda. So I want F lambda, the flux between wavelength ranges, between wavelengths lambda and lambda plus d lambda is F sub lambda d lambda. So I just want F lambda here. In terms of b lambda, we integrate over solid angle into the outward hemisphere. So in other words, the idea is set up the z-axis perpendicular to the surface, my little surface patch there. And I want to add up all the radiation going in every direction that is outwards from the surface. That's what I mean by integrating over the outward hemisphere. I integrate over all theta and phi that cover outward directions away from the surface. What that means is that F lambda, I want to integrate over solid angle over the outward hemisphere. F lambda is B lambda cosine theta d omega. And that's because what I want to add up is energy per unit wavelength interval per second per unit area. I want to add that quantity up because that's what flux is. Energy per unit wavelength interval per unit area. And from our definition of specific intensity where we've got dA cosine theta on the bottom, that means B lambda cosine theta is the contribution to the flux for each value of theta, is the idea there. Contribution to flux per unit angle theta, that ratio will be B lambda cosine theta. And I should really say there's also still the d omega down there as well, because that's into per steradian there, per solid angle. Sorry. I meant to put it over there, sorry. So in other words, that's what I'm integrating over there. When I integrate B lambda cosine theta d omega, I'm adding up all the energy per unit wavelength interval, per unit time, per unit area coming out of the surface in all the different directions. And then I'm just going to move over here to continue the calculation. So if I'm integrating over the outward hemisphere, I'm integrating over theta and phi, so I have to decide what ranges of theta and phi am I talking about. So if I'm integrating over every outward direction, what ranges of phi, what range of phi am I covering? 2 pi. What range of theta? Pi over 2, 0 to 2, pi over 2, right? Because I'm stopping at the horizontal. I only want outward radiation. So outward hemisphere says theta only goes to pi over 2. So this is phi is 0 to 2 pi. I'm doing all azimuth. Theta is 0 to pi over 2. B lambda cos theta. And then we have to remember that we decided that d omega, remember in spherical coordinates, was sine theta d theta d phi. So it's b lambda cosine theta, sine theta d theta d phi. So that's the integral I'm doing. And first piece is easy. The integral on phi, there's nothing about phi in the integrand, so I'm just integrating. I can factor that out. So the integral over phi gives 2 pi. So this turns into 2 pi times the integral theta equals 0 to pi over 2 b lambda cos theta sine theta d theta. And the happy thing is that's easy to do by substitution. And the usual, you could either use mu equals sine theta or mu equals cosine theta, but as we'll see, cosine theta is really important because it keeps, it shows up in the definition of specific intensity itself and so forth. So the standard thing to do is to use the substitution mu is equal to the cosine of theta. So then d mu is what? Minus sine theta, keep going. Minus sine theta d theta, right? You gotta have a d theta. There's gotta be a differential on both sides. Minus sine theta d theta. And then when we do an integration, when we do a definite integral, when we do a by substitution, we also substitute for the limits. So we want to know what mu of 0 and mu of pi over 2 are. Mu of 0 is 1. Mu of pi over 2 is 0. So there's a minus sign there, so let's just make it a plus sign and flip the limits. In other words, this would be 1 to 0 with a minus in front. Why not just call it 0 to 1 and get rid of the minus sign? So our integral becomes 2 pi, I can pull b lambda out. Integral from 0 to 1 of mu d mu. Because, right, that's minus du, that's d mu. So it's just mu d mu in good integration by sub. It's minus mu d mu, whoops, that's mu. It's minus mu d mu from 1 to 0 or plus mu d mu from 0 to 1. We're flipping the limits to get rid of the minus sign. I'm going to assert that that's an easy integral to do.
I can't do it.
Right. So, use math and go. So, the integral of mu d mu from 0 to 1 is 1/2. Right, it's mu squared over 2. Plug in 1, I get 1/2. So, this is pi b lambda. So, I just get pi b lambda. So, it's a very simple relationship. F lambda is pi times b lambda. F lambda is pi times b lambda. And so, a couple things and then we'll be done. So we've said that b lambda is 2hc, what was it again, 2 squared? 2hc squared over lambda to the 5th e to the hc over lambda kt minus 1. This says that f lambda, where you give it in terms of the total monochromatic flux coming out of the surface, f lambda just has an extra factor of pi in front of it. So that's 2 pi hc squared over lambda to the 5th e to the hc over lambda kt minus 1. That's f lambda. Flamda, yeah. Flamda and lambda.
Why didn't I think of this before?
I don't know, yeah. Yes, here in the history department, we've got Mike Flamda and his lecture on Lambda, that's right. And his lecture on explosive events, or if you like to say Lambda. Right? Flamda on Lambda, stop it. Anyway,
I'm sorry.
yeah. The 60s were an explosive time.
They were in here.
Yes, very lot of Lambda there. Yes. Never mind. Okay. And then meanwhile, remember that the total flux, which is integral from 0 to infinity F lambda d lambda, the total flux, says Stefan Boltzmann, is equal to Stefan Boltzmann law, which says the total flux is equal to sigma t to the fourth, sigma t to the fourth, right? Yeah, sigma t to the fourth. Since F lambda integrates to sigma t to the fourth, then if you integrate B lambda, you get sigma t to the fourth over pi. Since B lambda is F lambda over pi. Now
Lambda.
blank. Oh, damn, good word job.
Dang, never.
Dang, no. Damn, build it.
I had
Diego.
a meeting that I was supposed to be at.
Oh, whoops. Oh, you should have just cut out.
Yeah.